All right, so everyone can see the screen? All right, so is the screen visible for everyone? It's clear?
Yes, sir.
All right, okay, so we'll start. Before that, I did went through some of your quizzes. I did not get enough time to check all of them, as I was also I also gave quizzes to O levels and AS students. So I'll I'll check them by the end of this week, right? And then I'll share all of your quizzes back with all of you, and then we can solve the quiz in the class as well, right? Do you have any other questions regarding whatever we have done so far in this topic of ideal gases? Is there any question? All right, so I'll assume that there is no question. And last time we were solving a problem. What we did last time, we talked about the relationship between the molecule's speed and the pressure exerted, and we derived a relation for that, if you remember, right? So this is what we did. We derived a relation that relates pressure to the velocity of the molecule, right? So we took one molecule, and we solved that for this one molecule, and then we found a relation. We extended that to multiple molecules, right? And so that's where this mean value of the velocity squared came from. The next thing we started off was with a problem. And so I'll restate the problem, and so we can solve that. The problem is something like you have at a room temperature, which is 300 kelvins, and at room pressure, you have 1.0 into 10 raised to power 5 pascals, right? So these are just room temperature and pressures. You have a mole of gas, and this mole of gas at room temperature and pressure occupies a volume of 24 decimeters cube. The task was to compute the root mean square velocity, right? So we'll have to compute, well, if you just compute this thing, which is the mean square of velocity, then you can just take the under root of that, and then you'll get the root mean square velocity. So we have to compute this thing at this temperature, right? Which is the room temperature. We will do it for two different types of gases, which are made of molecules. So we have helium gas, right? So this gas is made up of helium atoms, and which have an atomic mass of 4 times U, right? And then let's do it for oxygen. But you have to remember here that oxygen is a molecule, right? And so the atomic mass of oxygen molecule is 16U, right? So I need the molecular mass of oxygen. So that would be 2 times 16, right? So that's 32U. So that's the problem, right? So can anyone tell me how will I compute this velocity, root mean square velocity? Note that we have pressures, we have temperature, and we have a volume that this gas is occupying at these pressure and temperatures, right? So anyone remembers anything that we did in the last lecture? So you can tell me, how will I go about this problem? By the way, is the statement of the problem clear to everyone? The class has become really quiet after Eid holidays. Anyone? Can anyone help me with solving this problem? All right, so I'll just give you a hint. I will just write that equation that we derived last time. That was P, which is pressure, was equal to 1/3 times N M V squared root the mean of V squared divided by the total volume, right? So that's the expression that we have. The task is to find out this thing. Let me just color it in green. So what is this thing in green? So that's what we want to find out, right? So of course, we'll write this as V square is equal to 3P times V divided by N times M. All right, so this is what we have now. We have pressure, right? We have pressure, we have volume, which is 24 decimeters cubed. What about this thing, N and M? Anyone? Okay, so N are these for helium gas, for example. Let's do it for helium gas at first. So N is 4, and we'll just multiply it with 1 mole of helium atom, right? So the total mass of helium atom is given by N times M, which would be what? 4 times 10 raised to power minus minus 3 kilograms, right? So are you getting how did I write this thing, NM? Because that's the only unknown at this point. I cannot hear you.
Could you go over this again?
All right, so yeah. We have this equation, right, for pressure and velocity, right? So an equation that relates these two things, and that's this equation that we derived last time. So we just rearrange this equation for this expectation value of velocity squared, and that's this expression. The problem is we don't know, or at least you might think that we don't know N and M, right? Because P and V, we know they are pressure, room pressure, and volume is 24 decimeters cubed. It's given. N and M, what is that? N times M is defined as the total mass of 1 mole of any atom, right? In this case, we are talking about helium atom, right? So Nm is the total mass. Nm is just N multiplied by M, right? It's the total mass of 1 mole of atom. Any atom, right? So 1 mole of any atom, you could say. So in this case, it is helium, because we are working this thing for helium. So, right. So that's where we have this 4 into 10 raised to power minus 3 kilograms, because this is 4 times U, right? So U is just the atomic unit, which if you want the total atomic mass in kilograms, U is just 1 into 10 raised to power minus 3. And so just 4 into 10 raised to power minus 3 kilograms is the total mass of 1 mole of helium atom. So that's where I have this 4 into 10 raised to power minus 3 kilograms from. So the next step is very simple. You just put in the values. 3 times pressure, which is given as 1.0 into 10 raised to power 5 pascals, times volume, which is given as 24 decimeter cube, divided by this thing, Nm, which is 4 into 10 raised to power minus 3 kilograms. You do the math and you get a value which would be 1.8 into 10 raised to power. We have 3 from here, 5 minus 3, and this is deci. So it will be 6, right? Meters square per seconds squared. So that's what? That's the expectation value of velocity squared, or you can say it's the mean of velocity squared. The question was to find the root mean square value, right? So we normally write it as RMS, and the root mean square value for this thing is simply the square root of this thing, right? It's just the square root of this value, which would be the square root of 1.8 into 10 raised to power 6. And well, you can work that out, right? So it's just the square root of this thing, right? And that's the answer for, or you can say that this is the root mean squared. This is the average velocity with which the helium atoms will be moving if they were put in a container where these conditions are met. 300 Kelvin is the temperature, and at 300 Kelvin, the pressure is 1.0 into 10 raised to power 5. So under these conditions, for example, if I were to lock the helium gas in this container, right? Here we have helium gas, and the temperature of this container is 300 kelvins, and at that temperature, the pressure is given as 1.0 into 10 raised to power 5 pascals, right? So if these were the conditions, and this volume of this container is 24 decimeter cube, in that case, every molecule or every atom of helium gas in this container would be moving with the velocity, which is this thing. Right? So is that clear?
Yes, sir.
All right. Okay. So the next part is for doing it for the oxygen molecule. It's extremely simple. You'll follow exactly the same thing. I recommend, I'll share these notes with you after the class as well. And I recommend that you do this part B, this one, by yourself, right? Try it doing yourself. And if you have any problems, we can discuss it in the next class, right? So after the class, I'll share these notes with you as well. So you can go through these and see. All right. So with this, let's move on to the next topic, which is the topic of relating temperature to the energy of these molecules, namely the kinetic energy, right? So we want to relate temperature and kinetic energy. Right? Okay, so really what happens is temperature is like a velocity. We all are familiar with this expression for kinetic energy, that it is given as half times mass times velocity squared, right? In general, whenever you're talking about mechanics, right? Simple classical Newtonian mechanics. The kinetic energy of any translational motion is given as this thing. Now, in thermodynamics or this matter physics, the analog of this velocity is really the temperature. Now, what that means is, because we know if velocity, if I have a particle and it's moving with some velocity, right? Now, if this velocity is a higher number, then we know that the particle would be moving fast, right? If the velocity is a lower number, then we know that the particle would be moving slow compared to any value, right? Similarly, in thermodynamics, that thing is communicated to you via temperature, right? So for example, I can again consider a box, and I have a molecule in this, and I apply some heat to this container, right? What that does is that will heat up the walls of the container. And what is happening really is that the container is obviously made up of atoms as well. So when I heat the walls of this container, those atoms start jiggling, right? Jiggling is a very informal word. They start vibrating and so on, right? And that is because, again, the heat or when the temperature rises, that is increasing the speed of these molecules, and that will eventually, if the internal thing is conductive, then it will eventually the heat will travel to this molecule, and what happens is then this molecule starts speeding up. So that means that, of course, temperature and kinetic energy are closely related to each other, right? So how can I find a relation between temperature and kinetic energy? So we can do that, and it's very simple. What we want to do is really we want to find a relation between temperature and velocity of the molecule, right? So if you remember, we have equation of state given as PV equals number of moles times RT. Right? So we have talked about this equation in detail. This is the equation of state for ideal gases, right? Where we gave some conditions, and if those conditions are met, we derived the relation. Now, if I want if I want a relation between temperature and velocity of the particle, then I have already derived a relation of relating pressure with the velocity, right? We did that over here, right? This was this relation. P is equal to 1/3 nmv, expectation value of v squared, divided by the volume. So, well, this is P, right? So if I bring this volume over here, then this becomes PV is equal to 1/3 nmv squared, like this. Now, if PV is this, right, then I can just, in this PV, I can write 1/3 nmv squared, like this, right? And this is equal to nRT. And clearly, this gives me a relation. We know if I take this thing, if I, well, it's, yeah.
What about the volume? You didn't write that down.
Oh, the volume, we brought it over here, right? So this, we're writing this in terms of PA in the place of pressure times volume, right?
Oh,
so
okay,
let me,
yes.
Yeah.
Yes, I got it.
You got it? Okay, good. All right. So, yeah. So now we just have to rearrange this equation a bit, and we'll find an equation that we are really looking for, right? And the equation is 3/2 kT. That's kinetic energy, right? We want this equation. Of course, I should have not shown you this equation before we derived it, but I did anyways. All right, so we just have to rearrange this equation. If I write this equation for 1 mole of gas, right? Suppose that I want this equation for 1 mole. Now, for 1 mole of gas, this equation, if I rearrange this, it becomes R times T divided by Avogadro's number, right? And we would have this thing is equal to, let's see, we have this thing RT, we have M and 1/3 and this thing. Right, so we just rearranged this equation, and we used the fact that N/N is Avogadro's constant. So is that clear? From this thing to this thing is understood?
Yes, sir.
Okay, good. All right, so we can make another simplification, and that simplification is that let's define a constant. I'll not name it yet, and let's say that this R/NA is this thing. Well, we know we can define this constant simply because of the fact that R is itself a constant. It's also called the gas constant, And Avogadro's number is also a constant. So you're just defining a new constant out of two other constants. And we can do that. That's allowed in mathematics. So this new constant was defined by Boltzmann, and it's given a name, Boltzmann constant. Right? So using this new definition of Boltzmann constant, what I can do is I can rewrite this equation as what? This R over NA becomes K, right? And then we have T over here. And then this is equal to 1 by 3 M, this thing, velocity squared. So is that clear for everyone?
Yes.
Now, okay, good. So, well, you can be done by this point. We can make another, we can write this equation in another way by simply dividing this expression by 2 and taking 3 over there. And the reason we'll do that is to make this equation look like the equation for kinetic energy, which is half mv squared. You can see that we have 1 by 3 m and v squared already over here. If instead of 1 by 3, I had 1 by 2 m v squared, then this would be like a kinetic energy, right? It would be exactly like the kinetic energy for the translational motion. So what I'll do is, I don't have more space on this page, so I'll just go to the next page and take this equation with me. So let's just do that. Copy. And let's put it over here. So this is the equation that we have so far. And now what I can do with this thing is I can play around by just really dividing it by 2. So I'll just say that I'm dividing this expression by 2. And once I do that, this becomes KT by 2 is equal to 2 by 3 mv squared. Now, it still is almost similar to half mv squared. Just take some things over there. So this becomes 3 by 2 KT is equal to half mv squared. Now, this thing we already know is the kinetic energy. It is the kinetic energy of any particle, half mv squared. If that's the kinetic energy and we have an equal to sign over here, then this thing is also a kinetic energy. And hence we deduce that the kinetic energy of 1 mole of gas is given as 3 by 2 kT.
Sir, how did that become half?
Which one?
Half m that v square. How did that become?
Oh, you mean this thing?
Yes.
Oh, yeah. Oh, just give me a second. I'll tell you. So basically, we have this thing, right? KT is equal to 1 by 3 mv squared, right? Now, I want 1 by 2 over here, right? So what I can do is first, let's just take this 3 over there. This becomes 3 KT. I kind of did this directly. So I think that's why there is confusion. I'll do it over here. This becomes 3 KT, right? And this is mv squared, something like this, right? Now you just divide this by 2. So you get 3 KT, 3 by 2 KT is equal to mv squared and 1 by 2. Is this clear now?
Yes.
Yeah, okay, all right. So, okay, so this is the kinetic energy, which is 3 by 2 kT. Now this is the kinetic energy of a particle that is moving in any environment, right? And it's given in terms of temperature. Now you can clearly see from this equation that if I increase the temperature, of course, 3 by 2 and K is constant. In physics, when you're doing physics, normally, and not at your level, of course, but normally what we do is we ignore all the constants. What we do is we set them, all the constants that are going to always remain constants, we just set them equal to 1, right? It's not equal to, but it's like you just say that they're 1, and at the end of this thing, you put them back in the equations. Because constants are not telling you anything about the physics of the situation. So if I ignore 3 by 2 and k, then I can see that kinetic energy is proportional to temperature, which means that as I increase the temperature, which we'll discuss how we can do that, you will increase the kinetic energy of the particle, right? So the relation that we were looking for is this one. All right, so is there any question up until this point from anyone?
No, sir.
No questions? Okay. All right, so I have a question for all of you, by the way. You all of you gave the quiz, right? Everyone gave the quiz who is in the class right now?
Yeah.
Yes.
All right. So how was the quiz? How did it go? Were you able to complete it in time, or did you find that there is less time and there were more questions? Anything of that sort? Just give me a general feedback on the quiz. That would be appreciated.
The time limit was fine.
Time limit was fine. Okay. And so how about the questions? Were you able to solve the questions having the knowledge that you gained from these classes? Were the questions
yes.
So you were satisfied with when you saw the quiz, you were okay that yes, we understood, we talked about these things in the class as well. Was it like this, or was it more like you know how it is, right? Well, the teacher never taught this to us and he gave us things out of syllabus, or was it like that?
No, it was from the syllabus, of course.
Yeah, of course, there are some things which they're still in the syllabus, but the things are given to you so that you know they allow you to work on your thinking skills as well. So that's also the motive behind it, really. So of course, we'll be discussing your quizzes very soon, hopefully by the end of this week, and you might I don't want to give you any surprise quizzes, so I will not do that. So just be prepared. In this week, by the end of this week, there will be another quiz on the very first chapter, circular motion. And if you were able to solve the quiz from gravitational fields, you'll be able to solve the circular motion. It's quite easy, nothing hard of that sort.
So tomorrow?
Yeah. Not tomorrow. I'll just say it will be on Friday, right? So I was going to tell you on after the class, finalize it and everything, but most probably it will be on Friday, right?
Oh.
Yeah. So I'll communicate it in the group as well. The topic or the chapter is circular motion, which was the very first chapter. So if you have any questions regarding anything from circular motion, you can, there is tomorrow. So you can, tomorrow is Thursday, right? So you can ask your questions tomorrow as well, if you're preparing today. All right. So, okay. So with that out of the way, now we have also derived this relation between kinetic energy and temperature. We've been using the word temperature a lot. Let's see what this thing really is. What is temperature, right? So let's move our discussion to the topic of what is temperature. Right, so we know that if I have a body and let's suppose we all are you all familiar with this fact that temperature is a field? Or are you hearing this thing for the first time? Okay, so I'll just explain the concept of fields as well to explain temperature. In mathematics, a field is defined as a set of operations. So it could be plus, minus, multiplication, and division. This set of operations is done on real numbers, and they'll give you a real number, right? So it's just something, it's just like a scalar, right? So you can do what this weird looking thing means is if I have 2 and I can do some operations on it. Those operations are plus. So for example, I want to add another number to this. I can do 2 plus 1. And these both are real numbers. So 2 is a real number, 1 is a real number. Adding these 2 numbers will give me 3. 3 is also a real number. So it belongs to this real field, right? So this gives me 3, which is again a real number. So what is happening is that if you take any real number and you do these operations on those real numbers, you come back to a real number. Now this real number is a real numbers field. Now this is how we also define scalars, right? So you might have heard a very, boring definition of scalars, and that's that they're just numbers and they have a magnitude but no direction. And I think that is the most boring explanation that you can hear for scalars. And then there is also for vectors that they have direction and magnitude, both. And that's also boring explanation. But of course, you don't have to go into the exotic descriptions of scalars and vectors. So, but here is just a touch of the interesting definitions of scalars, really. So this is how you also define scalar, right? Now, temperature is a scalar field. So it's a field in a room. For example, this is a room. And in this room, there exists this field at every point in this room. You can think of field as a fluid-like substance that is spread all across this room, right? So at every point in this room, you can assign a number. And you can say that this number measures how cold or hot is the room, right? So that's what temperature is. So at every point in this room, you can assign a number to this point, right? So I'm drawing multiple points. So suppose that here we have multiple points. Now, suppose in this room, there is a fire at one part of the room. So suppose that there's a fireplace over here, right? And in this corner of the room, there is a window. Now, of course, near the window, all the points that are near this window, the temperature would be low. The values, what I mean is the values at these points that I'm assigning, the numbers would be smaller. Compared to if I look at these points that are closer to this fireplace, these numbers would be high. And then once I check this, I'm defining temperature in this way. I'm saying where I have these numbers higher, that's where I say it's hot, right? So it's just a word of English. You just assign, you just say, yes, that this is hot. So that's what hot means. And cold is where this value is small. This number is small. That's what you call cold. So that's what temperature is. So is there any question, by the way, from what I've been telling you, or did you just get lost in all of this? Is it making sense?
Clear. Yes.
It's clear? Right. Okay. So the takeaway from this thing is that temperature is a field. It's really a scalar field, and it is you can think of it as a fluid-like substance. So let me just write this, all of these over here. So it's a field. Temperature is a field. It's a scalar field. And you can think of it, this field, as a fluid-like substance. And it's spread all over the room. Spread all over space, right? So, and these are just numbers. And the higher the number, higher numbers, so I'll just say numbers that are high, meaning this arrow pointing upward means high, corresponds to hotness, and this number being small corresponds to coldness. That's how you define temperature. Of course, then you can go into its philosophies and you can make more definitions and descriptions out of this thing. But this is really the most basic way you can define temperature. Right. So now suppose we have been talking in terms of just one body, right? This is just one body. Suppose that we have two different bodies. Suppose that you have, suppose this is body A and this is body B. All right. Now, what happens is, suppose that this body A is at some temperature T1 and this body B is at some temperature T2. Now, at this point, these bodies are separate from each other. What would happen? What would you think would happen if I were to bring these bodies so close that they touch each other? So suppose they are like this now. So this is A and this is B. What would happen to temperature of this entire system compared to the temperatures of these individual systems? What would you think would happen? Or what should happen? Anyone?
The one with the higher temperature will cause the one with the lower one to have a greater temperature.
Right, exactly, right. So that's very good, because and that happens why? Because